Hey, what's up, guys? Um, Last time I talked about rotation symmetry operations, so this time I'm going to talk a little bit more about rotation symmetry operations, just a couple more complex cases, and then we're going to talk about reflection symmetry operations. So first of all, just remember with symmetry operations, the point is you want to be able to put a molecule through this operation and then have it come out and be exactly the same as it was before it went in. So, for instance, let's do a linear molecule. Let's go with N2. Now N2, it has a rotation axis right down here that is a C2. Because obviously you can just flip those over 180 degrees and they're back the way they were. Now on the other hand, if you go straight down through both of the ends and down through the triple bond, you're going to have an infinity symmetry axis, because you can rotate it any amount and it's going to be the same. So the way we would designate this as a point group, it would be D infinity H. I'll draw that again. And we haven't gotten to this yet, but maybe you have in class. If you have two perpendicular symmetry axes, then you have a D point group. If you only have one main symmetry axis, you have a C point group. So this would be a D point group because you have a C2 on one end, and then perpendicular to that we have a C infinity axis. So that's a special case, and that's pretty much all linear molecules will have something like that. So let's look at carbon monoxide. Carbon monoxide has a triple bond, and you see there's no axis up here. We can't rotate that. But if we go straight down through this molecule, it again has a C infinity axis. So this point group is going to be C infinity V. Now, with these kind of linear molecules, you pretty much just have to remember they're either going to be D infinity H or C infinity V, just because there aren't that many of these cases, so at least that makes it easier. Okay, let's talk about reflection planes. So, one example that's always given right away with reflection planes is just a simple molecule like H2O. Now, you might remember, or you might notice right away, that H2O has a C2 rotation axis, right? But also, if you put a mirror down the middle right here, it would reflect perfectly across. And this is what we call a reflection plane. And in fact, this is only one of the two reflection planes in this molecule. And the other reflection plane, here, we'll draw water a little bit differently for this, so I can show you. The other reflection plane splits all three atoms. It goes right down the middle of them. So we can see they reflect the same on either side. So there's another one. Now generally this is a little trick that you can use, because sometimes you can get screwed up when you're calculating out for a character table for a molecule. The reflection plane that's listed first in the character table will go through the most atoms. That's usually just a nice little trick. So it just so happens that water's point group is C2V. So in my book at least, the C2V character table, for the first reflection plane, it's listed as sigma sub V xz. So that is the one, that's this one right here, because it goes through three molecules right there. Now, the second one is called sigma sub V prime and that is through the YZ axis. So as you can see, that's the second one. And just another note here, usually your primary rotation axis, that's designated as the Z axis. Okay, so one of these will be the X and one of these will be the Y. It depends on how your book does it, but normally the primary rotation axis is always the Z. So let's do another reflection plane one. Let's do NH3. How about we do NH3? Okay, now NH3, first let's look at the primary rotation axis. It's got a C3 right there, okay? And you might be tempted to say, yeah, it's got a C2 also, but it doesn't, because these aren't actually planar right here. So it's not going to have any other rotation axes. But it does have a reflection axis, and it's pretty much right in the same place where it would be for something that's trigonal planar like this. You'd say, oh, there's a C2 right through here. That's kind of where the reflection plane is for this. So if we draw NH3 from a straight up and down angle, you can see here is the reflection plane. That atom, the H atom, is stuck in the plane, so is the N, and the other two H's go through the reflection plane, look exactly the same after they come out. So, and the point group for NH3 would be C3V. And I know we haven't gotten to point groups yet, but you can see it doesn't have another rotation axis. It only has one rotation axis, and it only has one reflection plane, and it just has, so it only really has two symmetry operations besides E, and everything has the E symmetry operation. Okay, so finally for this video I'm going to look at the tetrahedral point group. It's called Td, and anything that's tetrahedral with all the same ligands is going to be in the Td point group, much like anything that's octahedral with all the same ligands is going to be in the OH point group. So methane, for instance, that's in the Td point group. Ammonium, NH4, that's in the Td point group. So, and Td's pretty complicated actually. You've got a lot of stuff going on. So let me just draw methane really quick. Now that might not be how you're used to seeing it, but if we rotate it, let me show you a quick way to look at some symmetry operations. Okay, so I rotated methane, so one of the hydrogens is going completely straight back into the page. So now we have a C3. You can see that C3 in there pretty good. Now the TD point group also has a C2 in it. And the C2 is a little bit harder to see, but if you put it like this, where you've got two facing you and two facing back, it's a little bit easier to see. You got a C2 in there. Okay. Now the best way to see the plane of symmetry in the TD point group is the same as the last one I drew, because reflection planes, they usually occur along a C2 axis. So you can see if I draw a reflection plane down the middle of this, there it is. It's as simple as that. So that's a couple different examples of reflection planes. Sometimes they're not always easy to see, but usually if you rotate the molecule enough and you look at all of the axes of rotation, you can start to see the reflection planes in the molecule. And so next video I'm going to talk about inversion centers, and we'll talk about all the other symmetry operations, the S operation, which is sort of complicated but almost you never have to worry about when you're solving out a character table. And then of course the E symmetry operation, which I haven't talked about yet. So, alright, see you next time.